Okay, let me do one more example and tack it on as a part 2 to that angular and linear velocity video. And we have sort of like a bicycle setup here. This could also be rotations of an engine and the final rotation of the back axle. All kinds of mechanical engineering type ideas with this little simple chain and gear setup. We've got, let's say this is a bicycle setup, and you're up here pedaling the bike, and you've got a front spoke with a chain going around it, and your pedaling is 25 rotations or 25 revolutions in a 30-second period, which would be 50 revolutions a minute. If you're pedaling 25 times in a full, doing 25 revolutions in 30 seconds, how many times is that back gear spinning to, turn that back wheel? I'm not going to do another, well, we're going to do a two-part thing. We're not going to talk about the entire outside diameter of the wheel, just how fast is that back sprocket turning if you're turning at 25 rotations every 30 seconds for the front sprocket. So, I'm not sure if this is the fastest way to do this problem, but it's how I'm going to do it. So, and the back sprocket is 6 centimeters as a radius. So, let's figure out what the angle velocity is for this front sprocket. Well, angle velocity is theta over time, theta, radians, degrees, not rotations. So 25 rotations times 2 pi, each full rotation is 2 pi or 360 degrees, but I'm using radians, over a 30-second period. Well, that's going to be 50 pi over 30 or 5 pi over 3 radians per second. Great. So this thing's turning at 5 pi over 3 radians per second. Well, this turning of the sprocket is pulling a chain. So whatever amount of chain you pull around the front sprocket is the same amount of chain you're pulling around the back sprocket. So what I want to do now is find out how much chain I'm moving in that 5 pi over 3 radians of rotation. So I want to find arc length, how much chain is getting pulled around that front sprocket. So, again for this front sprocket, S is equal to the arc, how much chain I'm pulling. It could also be, I could also just write V for linear velocity, how much is that front sprocket moved in 1 second. But I think, since my kids are thinking, okay, I'm pulling a chain around it, and that same amount of chain is getting pulled around the back, I found to do arc length instead of saying it's linear velocity makes it easier to understand. So the front sprocket is got a 15, let's say, centimeter radius, and in that, and that's the radius, so that's R. And theta for a 1 second period, theta is 5 pi over 3. So in 1 second, I'm doing R theta, so 15 times 5 pi over 3. The 15 and the 3 will cancel out to be 5. So 5 times 5 is 25 pi centimeters. And if I put per second, I need to call that linear velocity. So I'm going to just, again, say it's R times theta, but in 1 second you're pulling 25 pi centimeters of chain. Now, if you move 25 pi centimeters of chain through the front sprocket, then you have to move, and you are moving 25 pi centimeters of chain through the back sprocket, and we want the angular velocity of the back sprocket. Well, V which is RW, and so maybe just for clarifications for the video purpose, let's say that this is per second, and call this not arc length per second, but the linear velocity, the amount of chain you moved in 1 second. Linear velocity is equal to the radius times W. Well, in that 1 second period, you're moving again 25 pi centimeters of chain around a sprocket with a radius of 6, and V equals R and W is the question. What's the angular velocity per second? How much is the spinning per second if the front one is turning 5 pi over 3 radians a second? Divide both sides by 6, and that's 25 pi over 6 radians per second for the back sprocket. And that is a faster, that is a larger radian per second value than we have with the front sprocket, because of course it's smaller, so it's having to turn faster to move that same amount of chain that you're using or you're pulling around the front sprocket. So there you go, a two-part question going from linear and back to linear to angular velocity to linear velocity, and then back to angular velocity as you get to the other sprocket. I'm Mr. True. Bam! Go do your homework.